Good morning, good afternoon, and good evening to all of you. I'm Persia Ada N from the Department of Science and Technology, Industrial Technology Development Institute, and I'm here to talk about nanomaterials characterization and nanotechnology research in DOST-ITDI. The Department of Science and Technology is the executive department of the Philippine government responsible for the coordination and formulation of policies and projects in the fields of science and technology in support of national development. Shown here is the DOST organizational chart headed by Secretary Fortunato de la Peña. Under him are different offices, one of which is the Research and Development Institute. Under this are ASTI, FNRI, FPRDI, ITDI, MIRDC, PNRI, and PTRI. We belong to the Industrial Technology Development Institute, headed by Dr. Annabel Briones, which mandates are the research and development, technology transfer, scientific and technical services for the academe and the industry. Under ITDI, I will be discussing about the facilities and the researches in the Material Science Division headed by Dr. Blessy Basilia. The Material Science Division spearheads R&D programs on materials essential to the development of local industries, generates quality R&D while harnessing the use of locally available resources in developing various materials for industrial purposes, and provides world-class S&T services in material science and engineering. Material Science Division also houses the Nano Lab, which houses state-of-the-art machines for nanomaterial characterization. These are the nanolab facilities for membrane processing and characterization present in nanolab. Shown here are nanolab equipment for performance testing and coating characterization. Shown here are facilities for research and development. And here are nanolab equipment for materials characterization and identification. Most of this equipment are used for nanotechnology research. Another laboratory found in DOST under Material Science Division is the Advanced Device and Materials Testing Laboratory, where more advanced characterization tools are housed. Among the equipment there are listed here. We have the sample preparation tools, FTIR, differential calorimetry, and TGA. They also have time of flight secondary ion mass spectroscopy, 3D X-ray inspection system, OJ electron spectroscopy, and focused ion beam emission scanning electron microscope. Nanotechnology involves research and technology development at 1 nanometer to 100 nanometer range. We create new structures with novel properties because of their small sizes, and we build on the ability to control or manipulate material properties at the atomic scale. According to the International Organization for Standardization, or ISO, nanomaterial is defined as a material with any external dimension in the nanoscale or having internal structure or surface structure in the nanoscale. Nanoparticle is a nano-object with all three external dimensions in the nanoscale, while nanoscale is defined as the size range from approximately 1 to 100 nanometers. In nanoparticle characterization, what do we measure? We first look at the size. Okay? Spherical particles are described by a single size parameter, and if the particle is non-spherical, we measure at least 2 of the dimensions, and then we take the differential mean size and tabulate them as such. Okay, and in recording the particle size distribution, we measure at least 100 particles and then tabulate them, make a tabulated graph showing the size distribution of these 100 particles. The next is the shape or particle morphology. So whether it's spherical, rounded, angular, spongy, flaky, cylindrical, acicular, or cubic. The next property is the surface charge. Okay, we can actually measure whether the surface charge of a material is positive or negative, which affects how it reacts with the materials around it. Okay, listed here are characterization techniques for the physical and chemical evaluation of nanomaterials. So we have here the property or nanostructure property on the left, and then on the right is the characterization techniques that can be used. So for size distribution, and aggregation, you can identify them using TEM or transmission electron microscope, scanning electron microscope, atomic force microscope, and dynamic light scattering machine. For the morphology, we can use TEM and SEM. For topography, we can use AFM as well. For surface area measurement, we can use the Brunner Emmett and Teller machine or BET. For composition or chemical composition, we can use the XRF, X-ray fluorescence, ICP-MS, and the Raman spectroscopy. For phase information, we can use XRD and TEM. Surface chemistry, we have XPS, UPS, FTIR, TOF-SIMS, EDX, inverse gas chromatography. Surface charge and adsorption property, we can use the dynamic light scattering with the capability of zeta potential measurement, IR, and UV vis. And for the dissolution kinetics, we can use electrochemistry, ICP-MS, and SACS. So here are the experimental techniques used in nanoparticle characterization in ITDI. So first, on the left side, left column, we have the technique, and on the right column, we have the main information derived from these techniques. Okay, for X-ray diffraction or XRD, we can get the crystal structure, composition, and crystalline grain size of a material. For X-ray fluorescence, we can identify elemental composition. For Fourier transform infrared, we can identify surface composition and ligand binding. For Brunner, Emmett, Teller, or BET, we can measure the surface area of particles. For thermogravimetric differential thermal analyzer, or TGDTA, we can measure mass and composition of stabilizers. For dynamic light scattering, DLS, and zeta potential measurement, we can identify hydrodynamic size, detection of agglomerates, and of course the surface charge of the particle. For the transmission electron microscope or TEM, we can identify nanoparticle size, size dispersity, shape, aggregation, and we can identify also the crystallography of the material and identify if it's amorphous or crystalline, and actually identify what type of crystallography it has. For the scanning electron microscope, okay, we can identify morphology, the dispersion of nanoparticles in cells, and other properties. And for the atomic force microscope, okay, we can identify nanoparticle size, shape in three-dimensional mode. X-ray diffraction analysis, or XRD, is a technique to obtain crystallographic information about a sample by observing the diffraction pattern due to an X-ray beam hitting a sample. Shown here is an example of an XRD data. So you can actually identify the mineralogy of your material basing on this data. X-ray fluorescence analyzer determines the chemistry of a sample by measuring the fluorescence or secondary X-ray emitted from a sample when it is excited by a primary X-ray source. So we can do elemental analysis and oxide analysis of your sample. X-ray fluorescence analyzer determines the chemistry of a sample by measuring the fluorescence or secondary X-ray emitted from a sample when it is excited by a primary X-ray source. So you can do elemental analysis and oxide analysis. Fourier transform infrared spectrometer, or FTIR, determines the nanomaterial's molecular composition and structure of compounds by subjecting a sample to excitation of molecular bonds by broadband infrared radiation, and the Fourier transform mathematical technique is used to obtain the absorption spectrum. So shown here is an example of your FTIR data. Okay, and then we also have the thermogravimetric differential analyzer, or TGDTA. It's a technique in which the change of a sample is measured as a function of the temperature or time while the sample is subjected to a controlled temperature program. Dynamic light scattering particle size analyzer, or DLS, is a technique where the motion of particles in suspension causes laser light to be scattered at different intensities. Analysis of this data yields the value for particle size and the surface charge, or zeta potential, of your material. Scanning electron microscope, or SEM, is a technique that examines and analyzes the surface or sample by scanning with a primary electron beam, which causes the ejection of secondary electrons, backscattered electrons, absorbed electrons, and X-ray radiation. These signals can be used to determine the structure, composition, and the topography of your sample. Next, we have the field emission transmission electron microscope, or FETEM. It's a technique that produces images in diffraction pattern with the resolution in the atomic scale by using an electron beam which passes through the sample and interacts with the sample to a detector. So with our system, we can actually get the morphology, determine the crystallography of your material, and perform elemental analysis as well. Our laboratory has the atomic force microscope, electrostatic force microscope by Park system, where the AFM is a microscopy technique capable to create three-dimensional images of surfaces at high magnification, and EFM with Park AFM maps electric properties such as the surface potential and charge distribution on a sample surface by measuring the electrostatic force between the surface and a biased EFM cantilever. Shown here is the Material Science Division organizational chart. We are headed by Dr. Blessy Basilia, and under her are three sections, namely the Advanced Material sections, Special Materials section, and the Surface Engineering section. So we focus on different nanotechnology products, and we utilize mostly locally available materials, and produce nanomaterials from them and incorporate them in different materials, forming nanocomposite materials. Among the researches is polycarbonate layered silicate clay nanocomposites. Okay, the application of ITDI DOST developed nanoclay was conducted to produce the polycarbonate clay nanocomposite products such as plastic caps, tiles, sheets, and substrates for printed circuit boards. So as shown here are some examples of the products that were produced. We have plastic caps for current transformers, plastic tiles and sheets, and plastic substrates. Okay, the nanoclay that we developed in the laboratory increases the modulus and tensile strength at 3 to 5% loading compared to 20 to 60% loading of conventional reinforcing agents such as kaolin, silica, talc, and carbon black. So implicit advantages include lighter plastic parts with greater transparency. Another product that we produced is the Philippine halloysite nanoclay filled epoxy molding compound for integrated circuit packaging. The epoxy molding compound, or EMCs, are used for integrated circuit packaging, and one of the major components of EMC is the filler. So this study developed an epoxy molding compound using Philippine halloysite nanoclay as filler to improve the thermal properties of IC packages. So for the results, we observed that moisture absorption decreases with increasing halloysite content, and the high crack resistance with low glass transition temperature was observed as well. So the product produced conformed to operating temperature of the IC package with high decomposition temperature. Another research is the production of local bioactive polymer nanofiber scaffold for tissue engineering. The developed scaffold is made from local carrageenan blended with polycaprolactone. Nanotechnology was used to develop this third-generation biomaterial that provided scientific foundation for this novel scaffold for in situ tissue regeneration and repair, needing only minimally invasive surgery for disease treatment. The development of this biodegradable polymer having desirable cellular responses has been considered to be of great interest in the field of biotechnology or biomedical applications. The main advantage of using biodegradable polymers is that no second surgery procedure is needed in order to remove the scaffold that you embedded. Okay. One of my researches is in the synthesis of carbon quantum dots, or CQD. Okay. They are a new class of carbon nanomaterials with sizes below 10 nanometers. What's unique about this is its fluorescence mechanism. It has the ability to absorb energy, light, and heat, okay, and to emit photons or light as the electrons bounce back down to the valence band. So what's unique about this the color or the fluorescence depends on the size of the quantum dot. So for example, your quantum dot is in the range of 3 nanometers in size. It emits a green fluorescence, and as it grows, the size gets bigger. For example, it's in the range of 8.3 nanometers. It will emit a fluorescence of the a red colored fluorescence. Okay, for the properties, they are chemically inert. It is low toxicity. It's carbon material, so it's highly biocompatible, and it's low cost since the synthesis it's quite simple. Okay, for the promising applications, it can be used in biomedicine, optronics, sensors, and catalysis. Another research I'm doing is the synthesis of superparamagnetic iron oxide nanoparticles from black sand. So spions are small synthetic magnetite, hematite, and maghemite particles with size ranging from 10 nanometers to 100 nanometers in diameter. What happens is when we apply external magnetic field, it allows the particles to achieve their saturation magnetization and exhibit no residual magnetic interaction once the applied magnetic field is removed. Okay, as you can see here in the picture on the right, okay, this is a representation of your spion. Okay, we have zero valent iron in the core, mainly providing the reducing power for reaction with contaminants. Okay, we have an oxide shell which provides sites for sorption, and adsorption happens on the iron oxide surface while the magnetite possesses reducing power. The promising applications of spions are listed here, namely imaging and drug delivery, gene therapy, and gene delivery. So listed here are all of its probable applications. That's why we are interested in synthesizing this material from natural resources. That concludes my presentation for today. I'm now open for questions. Thank you.